Hello everyone, welcome back. Today we are tackling a classic binary search tree problem. Validate binary search tree, Leetcode 98. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given the root of a binary tree and we have to determine if it is a valid binary search tree. A valid BST follows following rules. For any given node, all the values in the left subtree must be strictly less than the node's own value. Similarly, all the values in the right subtree must be strictly greater than the node's value. What strictly means here is that both the left and right children values can't even be equal. They should be less than or greater than the root value respectively. And crucially, both the left and right subtrees must also be the valid binary search trees themselves. Now let's look at some examples. Here the root node is 2 and left child is 1, which is less than 2. So it follows the rule. But if this left child had children, they must also follow the rule and must also be less than root's value. Similarly, the right child of this node is 3, which is greater than 2. And again, if the right child had children, all of them should be greater than the root. And this tree perfectly follows the rules. So it is a valid binary search tree and we will return true. Then in example 2, the root is 5 and left child is 1, which is less than 5. So all good here. And right child is 4, which is less than 5. And because of this rule is violated, as the right subtree of the node must contain only the nodes with keys strictly greater than node's key, which is 5 here. And here 4 is not greater than 5. So this is not a valid binary search tree and hence we will return false. Alright, let's think about how we might solve this. The most intuitive approach that we might try out is to perform a simple recursive check following the definition of binary search tree, which says a node's value must be greater than its left child and less than its right child. So we start at node 5 and we ask, is 5 greater than its left child 1? And the answer is yes. And is 5 less than its right child 7? The answer to that is also yes. So this node passes. And then we go to its children, say to the left child first. And here we see that node 1 doesn't have any children. So no point of comparing. And hence we go to the right subtree where we see node 7. And again we check, is node 7 greater than its left child 4? And the answer is yes. And less than its right child 8? And the answer is yes to that as well. So this node also passes. And again, since node 4 and 8 don't have any children, there is no point in comparing and they also pass. So all checks passed. But is this tree a binary search tree? And the answer is no, as the node 4 is in the right subtree of root 5, which means it must be greater than node 5, but it is not. So this rule is broken. So this approach only ensures that a node is valid with respect to its immediate children and not its grandparents and ancestors and misses the big picture. So how should we fix this? Well, we want all nodes on the left to be less than the root and all nodes on the right to be more than root, and we have to do it recursively. So we again start from the root node and check if the entire left subtree is less than 5 using some helper function. Say is subtree less than the value where we will pass in the node's value, which is 5 here. So we check if the entire left subtree, that is node 1 and its children, are less than the root node 5 and the answer is yes. Similarly, we will check if the entire subtree on the right is greater than root value 5. Again, using some helper function, say is subtree greater than the root value. So it will check node 7, which is more than 5, so all good. Then we go to node 4. Is it greater than 5? The answer is no. So this function will return false. And because of this, we will detect that this tree is not a binary search tree. But suppose instead of 4 here, we had value 6, then this check would have passed. So we go to node 8 and it is also more than 5. So all the values on the right for the root node 5 are greater than 5. So all good here. But we are not done yet. We should repeat this process for all nodes in tree because we have validated the binary search tree check for just the root node. But there can be violations for other nodes in tree. For this tree to be a valid binary search tree, this property must hold true for all its subtrees. So we have to repeat the same process with, for example, node 1 as the root. Then we have to repeat the same thing for node 7. And we have to keep repeating this process for all n nodes. Now checking if all the nodes on the left or right are less than or greater than the root value takes O of n time, and we are repeating this process for all the n nodes. Hence, the time complexity of this approach will be O of n square, and the space complexity will be O of h, where h is the height of the tree, as the function uses recursion depth proportional to the height of the tree, which in the case of skewed or unbalanced tree will be O of n. Now even though this approach works, it is super slow due to the time complexity of O of n square, as we are revalidating the same nodes again and again, checking if they are larger or smaller than the particular value. Can we somehow check them only once? The core BST rule is that for any node, everything in its left subtree must be smaller and everything in the right subtree must be larger. This means we can carry a valid range, a lower bound and the upper bound that each node must fall into. For example, when we go to the left, these values must be less than the root value. Hence, their upper bound is dictated by the root's value. Similarly, when we go to the right, the values must be larger than root. So their lower bound is constrained by root's value. So again we start at the root node with value 5. And since it can be of any value, its valid range is from negative infinity to positive infinity. So this value 5 is fine. And hence we recurse to its children. Say we go to the left child first. Now, since we went to left subtree, all the values must be less than the parent. And here parent's value is 5. This 5 becomes the new upper bound. And the lower bound doesn't change. And it stays negative infinity. And now we check if node 1 is within the range of negative infinity and 5. And the answer is yes. So it is a valid node. Next, we check its children. Say we go to the left child first and it is null. And this is our base case as well. When we see a null node, we treat it as valid because it doesn't have any value. So it can't be checked against any range. And same is true for its right child, which is also null. So we will return true for both its children. And now node 1 is fully validated. And we move back up and go to the right subtree where we see node 7. And now again, as per binary search tree rules, all the node values on the right must be greater than their parent. So 5 becomes new lower bound for node 7. And then we check if node 7 lies between 5 and positive infinity. And the answer is yes. So it is a valid node. And that's why we go to its children. Say first to the left child. And since we went to left, it must be less than the parent 7. And this defines the new upper bound. And notice that it must also respect the existing lower bound of 5 passed down from its grandparent, as this grandchild is on the right of it. So now we have to check if 4 lies between the range 5 and 7, and the answer is no. So we will return false. And this shows that our algorithm is correct. Now let's look at the positive case. Suppose instead of 4, here we had node 6. Then we can see that 6 lies between the range 5 and 7. And hence it is a valid node. So we recurse back and go to the right child of 7, which is node 8. And it must be greater than the parent 7. So the new lower bound for this node will be 7. And upper bound says infinity. So again we check if 8 lies between 7 and infinity. And the answer is yes. So it is also a valid node. And now we have visited every node and all checks passed within their required range. And the algorithm returns true. So we have successfully validated the tree in a single efficient O of n pass. So because of this, the time complexity of this approach is O of n, and the space complexity will be O of h, because again we are using the recursion stack, and in the worst case for the unbalanced tree, it will be O of n. Let's now walk through the optimal code with Java code on left and Python on right. We start with the DFS with the root node and initial ranges minus infinity and positive infinity. For that, we'll use a helper function which takes in the node and the allowed bounds for the node. Note that in the Java code, we are using long type for both min and max boundaries. This is a clean trick to handle potential edge cases where a node's value is exactly integer.min value or integer.max value. By using long, our initial boundaries are guaranteed to be outside the node's integer value range. An alternative approach is to use integer object wrapper class instead of the primitive long. In that case, we can pass null to represent infinity for the initial minimum and maximum bounds. However, this requires adding null checks in our validation logic to avoid null pointer exception before we compare the node's value with the bounds. So, we will continue with the primitive long approach. If you are interested, I have also shared that code. It is available in the code link in the description below. And in Python, we can use floating infinity. And now in the helper function, first thing we check is the base case, where we check if the current node is null. If it is, that means we have reached the end of the branch, which is valid by definition. So we return true. Next we check if the current node's value respects the bounds passed to it. If not, we will return false. So in Java, we check if the value is not strictly greater than minimum or strictly less than maximum. In that case, we can return false. And in the Python, this core validation is very clean. We just check if node's value is strictly within the min and max bounds. If it is not, we return false. Otherwise, if the current node is valid, we need to check its children. For the left child, the lower bound stays the same, but the upper bound becomes the current node's value. This ensures everything in the left subtree is smaller. And for the right child, the upper bound stays the same, but the lower bound becomes current node's value, ensuring everything to the right is larger. And finally, we return true if both the left and right recursive calls return true. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.